Section 7.1, Polynomial Functions and their Graphs. In this section, we will identify polynomial functions, identify features of the graphs of polynomial functions, including degree and leading coefficient, turning points, relative and absolute extrema, end behavior, location and multiplicity of the real zeros of the function, and determine any complex zeros of the function. We'll see how to sketch the graph of a polynomial function, and turning the idea around, model a polynomial function given a graph. We'll see an application of a polynomial function, and then we'll go on to discuss polynomial division, including long division of polynomials, the division algorithm, synthetic division of polynomials, and the remainder theorem. So first, what is a polynomial function? A polynomial function of degree n is one of the form f of x is a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a sub n minus 2 x to the n minus 2 plus a sub 2 x squared plus a sub 1 x plus a sub 0, where n is a non-negative integer and all the a sub n through a sub 0 are the coefficients of f of x, and a sub n is non-zero. Alright, so degree n, notice that will be the highest degree on the variable. We call a sub n x to the n the leading term of the polynomial. We call a sub n the leading coefficient, and a sub 0 is called the constant term. Alright, so let's see a couple of examples. Are these polynomial functions? If so, identify the degree, leading term, leading coefficient, and constant term. So for f of x equals 11 minus the square root of 6 times x to the 4th minus x squared minus 1.6x cubed. Is it polynomial? Well, I could rewrite it in the form negative root 6 x to the 4th minus 1.6x cubed minus x squared plus 11. So it appears to be in a polynomial form. Notice we're missing an x term, and so we could understand that there's a 0x term. So this is a polynomial. Notice how on x we have x to the 4th, and that's a non-negative integer. X to the 3rd, that's a non-negative integer. X to the 2nd, non-negative integer. So yes, this is a polynomial. The degree of the polynomial is 4. The leading term is negative root 6 x to the 4th. The leading coefficient is negative root 6, and the constant term is 11. Alright, in the second example, we have negative 82x squared plus the square root of 2x cubed minus 1.6x to the negative 1st. This is not a polynomial. If we look at this term, we have this negative 1.6x to the negative 1st. The exponent, negative 1, that is not a non-negative integer. So f of x, the second example, this is not a polynomial. Now we're going to look at some features of polynomial functions. So we're going to start by graphing a function, 3x cubed minus 2x squared minus 27x plus 18 on the calculator. We're going to use the function, the graph, and the calculator tools to identify some features. The degree and leading coefficient, we can identify those already. The number of turning points, location of the relative or absolute extrema, and end behavior. Alright, so let's go to the calculator. The function is 3x cubed minus 2x squared minus 27x plus 18. Let me check my window. I'm going to start in the standard window, so let me go from -10 to 10 by 1s on the x, and same thing on the y's, -10 to 10 by 1s on the y, the standard window. Alright, and so I see some stuff here. It looks like if I'm moving from left to right, it appears to be increasing. Now I think somewhere up here there's going to be a turning point, and then it's going to decrease, and have another turning point, and then it'll increase again. Alright, so let me change my window. The important values for x appear to be between 1, 2, 3, -5 and 5. So let me look from -5 to 5 on the x, and on the y's, let me try how about -30 to 30 on the y's, and I'll change my scale to tens. Alright, that's a little better. I see a better picture. Let me increase the y max just a little bit more to get a better picture. Let's go to 40 on the y max. A little more. 50. That should do it. Alright, so I see a fairly good picture of this graph. Alright, now what's the degree? So I actually didn't need the calculator for this. The degree is 3. The leading coefficient is also 3. The degree, right, and the leading coefficient. What is the number of turning points? Well, looking at the graph, we see a turning point. Now, a turning point where it changes from increasing to decreasing or vice versa. So I see 1, 2 turning points. So I see 2 turning points. Any relative or absolute extrema? Again, looking at the graph, there's no absolute extrema. This graph is going to, if I were to move to the left, it would keep on decreasing. If I move to the right, it will keep on increasing. But I see a relative max, and we can calculate that using the maximum command. So remember to find the relative max. You move to where you think it is, move a little bit past where you think it is, hit enter, move to the right, go past where you think it is, hit enter a second time, move back towards where you think it is, and hit enter a third time. So there's a relative maximum of 43.88. Right, so we have a relative max of 43.88 when x equals -1.52 approximately. And going back to the graph, we see a relative minimum of about -20.02. And that occurred when x was about 1.97. And now what about the end behavior? So if we look at this graph, what we see is it's moving downward to the left, and it's moving upward to the right. So here's how we would say this. As x approaches, as x tends to -infinity, as I move far to the left, the function f of x also approaches -infinity. As x approaches +infinity, the function approaches positive infinity. Alright, so as x approaches negative infinity, that's far to the left, right? The function goes to negative infinity, down. As x approaches positive infinity, as we move to the right, the function approaches positive infinity, up. Here's another function. F of x is x to the fourth minus 50x squared plus 49. And we're going to do a similar process. Maybe now would be a good time to pause and try this one out on your own. Alright, so let's go to the graph, my y equals screen, and clear this out. I have x to the fourth minus 50x squared plus 49. And let me go ahead and I'll go back to the standard window to start. So I'll hit zoom 6 to go back to the standard window. And I see, oh gosh, it almost looks like I have 4 vertical lines at what, -7, -1, 1, and 7. So let me keep my x's the way they are, and let me change my y minimum and maximum. Let me go from, I don't know, how about -50 to 50 on the y's, and see if I get a better picture of the graph. And I'll change my y scale to 5s. Alright, so I see looks like I see a maximum here. Alright, but I need to adjust this a little bit more. Let me try adjusting the y minimum some more. Let's go to -100 on the y minimum, and I'll go ahead and change my scale to 10s now on the y's. That's a little better. It looks like it's, as moving from left to right, it appears to be decreasing, then increasing, decreasing, then increasing. I need to adjust the window some more. Let's go to, how about -200, and see if that gives me a better picture. That's a little better. Let's go a little further. How about -400? And while I'm here, I'll change my scale to 25s. Almost there. About -500 on the y minimum. A little further. This is something you have to do sometimes. Okay, now I've got a better picture of the graph. And as I move from left to right, the function appears to decrease, turning point, increase, turning point, decrease, turning point, increase. So from what I can see, the degree is 4, right? The degree is 4. The leading coefficient is 1. The number of turning points, as shown in the graph, there was 3 turning points. Any relative or absolute extrema? Well, I see, right, decreasing, I see a relative maximum. Let me calculate that relative maximum. It appears to be when x is 0. Let's just verify that. -2.609 e to the -6. So remember that scientific notation, e to the -6. So that's -0.000026. So that's pretty close to 0. And the y value there is 49. So it appears that I have a relative max of 49 at x equals 0. Alright, what about those minimums? Alright, so move past it, hit enter. Move to the right of it, hit enter. And as a guess, somewhere in the middle, hit enter a third time. And that's -576. So there appears to be and there doesn't appear to be any points below it, so it appears that there's an absolute min of -576 at x equals -5. And if you just sort of trace, I'm going to hit trace 5 for x equals 5, and I see that when x equals 5, the y value is also negative 576. We have an absolute minimum of negative 576 at x equals 5 and, x equals negative 5 and x equals 5. Now the end behavior. So what is happening as we move far to the left? Well, let me adjust my window a little bit more. Let me change the y maximum to, how about 200 now? Just so you can see a better picture. So notice as I move far to the left, the graph appears to be increasing, moving up to positive infinity. And as I move far to the right, again, the graph appears to be moving to positive infinity. So we would say, as x approaches negative infinity, f of x approaches infinity. And as x approaches positive infinity, that function again approaches infinity. So again, what does that mean? As we move to the left, the function moves up. As we move to the right, the function moves up. So in those last two examples, we use the calculator to see some features of the graphs and find them. Now we're going to go and discuss different possibilities and try to arrive at some conclusions regarding polynomial functions. So what does a degree 1 polynomial look like in general if you graph it? Well, really there's two possibilities. If we assume, there's two possibilities. We can have an increasing function, an increasing line, or we can have a decreasing line. Those are really the only two possibilities. All right, so degree 1, that means your function f of x is ax plus b. Well, degree 2, f of x equals ax squared plus bx plus c. Well, those are quadratics, so not worrying too much about whether it opens up or down, what we've seen is we have three possibilities. Really, we could have a graph that does like this. We could have a graph that does something like this. We could have a graph that does something like this. I'm just sort of worrying about location. Degree 3, we haven't worked too much with degree 3 polynomials, but what we have seen is they can do things like this. Right? Sort of having a center point. Right? We talk that as the transformation of f of x equals x cubed, which is a degree 3 polynomial. We can also have it do something like this. And we could have something like this. So those are some different degree 3 polynomials. What about degree 4? Well, degree 4 polynomials, we could have a function. We can actually have degree 4 polynomials that look almost like a degree 2, like a parabola. Maybe a little bit flatter. But you can also have degree 4 polynomials that do this. And degree 4 polynomials that do this. And degree 4 polynomials that do this. And we can move them, shift them around, flip them over. We can do all that sort of stuff. But let's look at something. Let's look at the zeros, the x-intercepts. When we have a degree 1 polynomial, we could only have one x-intercept. A degree 2 polynomial, we could have 2, 1, or none. Degree 4 polynomial. I'm sorry, degree 3. We could have 1, we could have 2, we could have 3. Degree 4 polynomial. We could have 1, 2, we could have 3, we could have 2, we could have 4, we could even have 0. I didn't show that example. A degree 4 polynomial that we could have a degree 4 polynomial that does this and has no x-intercepts, no zeros. So a conclusion regarding zeros. One conclusion we could reach is that the number of zeros is less than or equal to the degree. Right, so if we know the degree of a polynomial, the number of zeros is less than or equal to the degree. Conclusion regarding turning points. Well, let's see. A degree 1 polynomial can't have any turning points. It's a line. For a degree 2 polynomial, a quadratic function, a parabola, we could have 1 turning point. For this degree 3 polynomial, here are some of the possibilities. This had none. This had no turning points. This graph has 1, 2 turning points. This graph has 2 turning points. And for the degree 4 polynomial, let's see, we could have 1. This graph had 3. This graph has 1. This graph has 3. This graph has 3. This graph has 3. So, conclusion regarding turning points. Degree 1 had none. Degree 2, we could have 1. Degree 3, we could have none or 2. Degree 4, we could have 1 or 3. Conclusion regarding turning points. The number of turning points is at most 1 less than the degree. So a degree 4 polynomial can have at most 3 turning points and at most 4 zeros. So here we have this nasty looking function. We're asked to find the zeros of the function and to state the degree. Now let's look at this function. We have f of x equals 5x by x minus 7 squared by x plus 11 cubed by 2x minus 5. Now if I were to multiply that whole thing out, and I don't want to do that, but if I did, I could get a polynomial function out of it. But I don't want to do that. If I'm asked to find real zeros, well, I set the function equal to 0 and solve the resulting equation. So that means I'd have 5x by x minus 7 squared by x plus 11 cubed by 2x minus 5 equals 0. Well, this is just a product of numbers equaling 0. So to solve an equation where we have a product of numbers equaling 0, we set each of the factors to 0. So now where is 5x equal to 0? Well, 5x equals 0 if x equals 0. Where is x minus 7 squared equal to 0? X minus 7 squared equals 0 only if x minus 7 equals 0, which means that x equals 7. X plus 11 cubed equals 0 only if x plus 11 equals 0, which means that x equals negative 11. And 2x minus 5 equals 0, that means that 2x equals 5, which means x equals 5 halves. So there are 4 real zeros of the function, and they are at 0, 7, -11, and 5/2. State the degree of the function. So we have this function Now, if we were to multiply this all out, the first factor contributes an x to the first. Right? We have 5x. That's an x to the first. The second factor, x minus 7 squared, contributes an x squared. The third factor contributes an x cubed. And the fourth factor contributes an x to the first. So if we were to multiply all of those together, we would have an x to the 1 plus 2 plus 3 plus 1. That's an x to the 7th. So this is a degree 7 polynomial. And notice that the number of zeros, 4, is less than 7. So that fits within our first conclusion on the previous slide. So we've talked a little bit about number of x-intercepts and turning points. Let's consider the behavior near the x-intercept. We're going to go back to some simple examples. If we sketched y equals x minus 2, well, that's a line with an x-intercept of 2 and increasing. So notice it passes through the x-intercept of 2. Now, if we had x minus 2 squared, that's just a transformation of y equals x squared. And so we would get a graph that does this. It touches the x-intercept, but doesn't pass through. It sort of bounces off. X minus 2 cubed, we saw that as a transformation of y equals x cubed. And so we would have a graph that does something like this. It increases, flattens out, passes through, and increases. So notice it passes through the x-intercept of 2, but flattens out near it. And if we had x minus 2 to the 4th, now we haven't done much work with, x to the 4th, but if we sort of follow the pattern, what will happen here is it'll decrease, it'll flatten out, but then bounce off. So, conclusion regarding behavior near the x-intercept. So notice that this x minus 2, that's an x minus 2 to the first power, that first one that we did. X minus 2 to the first. So notice, odd, odd, passes through, even, even, does not pass through. Alright, so what we have here is, these are factors with different multiplicities. So if the multiplicity is odd, pass through the x-intercept, if the multiplicity is even, do not pass through. The x-intercept. And we can also go a little bit further. We can say that the curve flattens out near the x-intercept for larger multiplicities. All right, now what about end behavior? Well, if we have y equals x and y equals negative x, y equals x looks like this, and y equals negative x looks like this. Yx squared and negative y and y equals negative x squared. Y equals x squared, parabola, opening up, vertex at 0, 0. Y equals negative x squared, parabola, opening down, vertex at the origin. Y equals x cubed and y equals negative x cubed. Y equals x cubed, negative x cubed, y equals x to the fourth, and y equals negative x to the fourth. Poorly drawn. So, end behavior. Notice degree, the degree on the left examples, the degree was odd. On the right examples, the degree was even. So, for odd degree, notice if the lead coefficient, let's look at the lead coefficient. The lead coefficient was positive, positive, negative, negative. Odd degree, and then if the lead coefficient is positive, as x approaches negative infinity, f of x approaches negative infinity. As x approaches infinity, as x approaches infinity, f of x approaches infinity. All right, so that's lead coefficient greater than 0. So that's these cases. If the lead coefficient is less than 0, that's these cases. As x approaches negative infinity, that just sort of flips. F of x approaches positive infinity. And as x approaches infinity, f of x approaches negative infinity. So one thing that's important about odd degree polynomials is their end behaviors are different on the left and right. Whereas now if we consider the even degree polynomials, notice that for y equals x squared and y equals x to the fourth, they had the same end behavior on both sides, up and up. So for an even degree, with a positive lead coefficient, as x approached negative infinity, the function approached infinity. As x approached positive infinity, the function also approached positive infinity. And for a negative lead coefficient, it just flips over. As x approaches negative infinity, the function approaches negative infinity. And as x approaches infinity, the function also approaches negative infinity. So putting all of that together, properties of polynomial graphs. For the polynomial function of degree n, these properties apply. The domain is a set of all real numbers. The graph has at most n minus 1 turning points, 1 less than n. The graph has at most n x-intercepts. So if the degree is n, there can be at most that many x-intercepts. Now those intercepts may have even or odd multiplicities, which we talked about. End behavior. Odd degree polynomial. One end points up, one end and the other end will point down. If the leading coefficient is positive, the right-hand side will point up, which means the left-hand side will point down. If the leading coefficient is negative, the right-hand side will point down, which means the left-hand side will point up. If we have an even degree polynomial, the end behavior will reflect the following. Both ends will point up or down. If the leading coefficient is positive, both ends point up. If the leading coefficient is negative, both ends point down. Alright, so we have all that information, but sometimes we still need to be able to find the zeros. Now we saw one example of that where we had this form that was already factored. What if we had to find the real zeros of f of x equals 2x cubed plus 7x squared minus 15x? Well, what we want to do is solve 2x cubed plus 7x squared minus 15x equals 0. So I'm going to use some factoring. That's x by 2x squared plus 7x minus 15 is 0. Now I've got to try to factor that remaining trinomial. So using whatever method works for you, I know there's going to be a 2x and an x, so that multiplies to 2x squared, and now I'm working with the 15. 5 times 2 is 10, and 3 times 5 is 15. 5 times 2 is 10. 3 times 1 is 3, and 10 minus 3 is 7. So now I just got to make the signs work. 2x times a positive 5 will give me a positive 10x, and a minus 3 will give me a minus 3x. There's a 7x is 0. Now you can also use an AC method or a cross factor method, whatever method works for you. You can look those things up, those techniques up. Now we have a factored form equal to 0. We set the factors to 0. X is 0. 2x minus 3 is 0, which implies that x is 3 halves. X plus 5 equals 0, which implies that x equals negative 5. So the zeros, the real zeros, then are negative 5, 0, 0, 0, and 3 halves, 0. Let's look at another exercise. Here we have f of x is 3x cubed minus 2x squared minus 27x plus 18. So I want to solve 3x cubed minus 2x squared minus 27x plus 18 is 0. So I need to try and factor this. I'm going to use the grouping technique. So we group together the first two terms, and their common factor is x squared. So that's x squared by 3x minus 2. We group together the second two terms. Their common factor is negative 9. Negative 9 times 3x minus 2 is negative 27x plus 18. So this factors further as 3x minus 2 by x squared minus 9. And that x squared minus 9 factors as x plus 3 by x minus 3. So I have 3x minus 2 equals 0, which implies that x equals 2/3. I have x plus 3, which equals 0, implying that x equals negative 3. And I have x minus 3 equaling 0, which implies that x equals 3. So I have 3 x-intercepts, 3 zeros, at negative 3, 0, 2/3, 0, and 3, 0. Now let's take a closer look at that last example where we're asked to find the real zeros of 3x cubed minus 2x squared minus 27x plus 18. We saw that the real zeros were at negative 3, 2/3, and 3. And we got that from factoring the polynomial. And so what we saw was the factored form, right? We had factors of x plus 3 3x minus 2, and x minus 3. And so you notice that there's a relationship here. Now that 3x minus 2, that one doesn't seem to match very well with the other ones. But notice for something here. X plus 3 is the same as x minus negative 3. And x minus 3 is the same as x minus 3. Now 3x minus 2, I can write that as 3 times x minus 2/3 if I really wanted to. And so that x minus 2/3, if we look at that factor, that's x minus 2/3. And notice something here. Negative 3, 2/3, 3. If we look at those factors, there is this relationship between the factors and the x-intercepts, and it works every single time. And we call this the factor theorem. If f is a polynomial function, then x minus k is a factor of f if and only if f of k equals 0. And we can look at this. Notice we had the factored form. Notice that we had the function f of x, this function. We had this function as 3x minus 2 by x plus 3 by x minus 3. Notice, what is f of 3? F of 3 would be 3 times 3 minus 2, that's 7, times 3 plus 3 is 6, times 3 minus 3 is 0. 7 times 6 times 0 is 0. F of 3 is 0. F of 3 is 0. That implies x minus 3 is a factor. If f is a polynomial function, x minus k is a factor if and only if f of k equals 0. And we can turn that around. If f of k is 0, x minus k is a factor. Is x plus 4 a factor of f of x equals 2x cubed minus 8x squared plus 3x minus 12? How could we check this? Notice that x plus 4 is the same as x minus negative 4. So my k value is negative 4. Let's evaluate f of negative 4. F of negative 4 would be 2 by negative 4 cubed minus 8 by negative 4 square plus 3 by negative 4 minus 12. That would be 2 by negative 64 minus 8 by 16 plus 3 by negative 4 minus 12. That's negative 128. Negative 8 times 16 is negative 80 plus 48. That's a negative 128 minus 12 minus 12, which is negative 256 and 48. That's a large negative number. It's negative 280. So, since f of negative 4 is not 0, x plus 4 is not a factor. check another value. What about the factor x minus 4? Let's see if x minus 4 works. So let's go back. Let me erase some stuff here. So now with x minus 4, that means that my k value is 4. And so f of 4 would be 2 times 4 cubed minus 8 times 4 squared plus 3 times 4. And so that would be 2 times 64 minus 8 times 16 plus 3 times 4 minus 12. That's 128 minus 128 plus 12 minus 12, which is 0. Since f of 4 equals 0, x minus 4 is a factor. What if we're asked to find real and imaginary zeros of a function? Alright, well, let's look at this function. We have 5x cubed plus 9x squared plus 45x plus 81. So we would still set it equal to 0. I'm going to try and use some factoring here. I'm going to use that grouping technique again. That's the first two terms have a factor of x squared, so I can write them as x squared by 5x plus 9. And the second grouping has a factor of 9. And so I have 9 times 5x plus 9. So that factors further as 5x plus 9 by x squared plus 9 is 0. So that implies that 5x plus 9 is 0, which means x equals negative 9/5, or x squared plus 9 equals 0. Now, x squared plus 9 doesn't factor. I can write this as x squared equals negative 9, and then using the square root property, I have x equals plus or minus square root of negative 9. Now here we have to be careful. That square root of negative 9 is the same as the square root of 9 times the square root of negative 1. And so we can write then that x equals plus or minus 3i, where I is the imaginary unit. So there are 3 zeros to the function. One real, right? We have a real 0 at negative 9/5, and we have 2 imaginary zeros at plus or minus 3i. Alright, so now that we've talked about the different behavior of the polynomial functions and the zeros, now let's get down to sketching the graph. In general, here are some ideas for sketching a polynomial function with real zeros. We want to find and plot the y-intercept. We determine end behavior by looking at the degree and the sign of the leading coefficient. We find all of the real zeros and multiplicities, and we use some test points between the real zeros to help draw a smooth curve. Sketch the function f of x equals negative x by x minus 5 by x plus 2. Alright, so the first thing I'm going to do is find the vertical intercept. Right, to find the y-intercept, we'll evaluate f of 0. And f of 0 would be the opposite of 0 by 0 minus 5 by 0 plus 2, and that's 0. So the y-intercept then is 0, 0. Second, let's look at the end behavior. Well, the degree of the polynomial. This is an x to the first, an x minus 5 to the first, and x plus 2 to the first. So I have a degree of 1 plus 1 plus 1. The degree is 3. If I were to multiply the whole thing out, I would have a negative x cubed. Right? So the lead term would be a negative x cubed, which means that the lead coefficient is -1, which is less than 0. So that means my end behavior, since I have an odd degree and a negative lead coefficient, that means as I move far to the right, it's going to move downward, and that means far to the left, it's going to move upward. Let's find the x-intercepts, the zeros. Setting the function equal to 0. I have negative x by x minus 5 by x plus 2 equal to 0. That implies that negative x equals 0, which implies x equals 0. X minus 5 equals 0, which implies x equals 5. And x plus 2 equals 0, which implies that x equals -2. So I have 3 x-intercepts at the origin, at -2, and at 5. I have 3 x-intercepts. I have the y-intercept at the origin, but I've already plotted that point. My end behavior is upwards to the left, so a little bit to the left of the last intercept, it's moving upward. And a little bit to the right of the rightmost intercept, it's moving downward. Now what happens in between? Well, let's look at each of the intervals. So how about we evaluate f of, say, -1? So here's sort of a test point. If f of -1, I have -1, -1 minus 5, -1 plus 2. So that would be 1 by -6 by 1. That would be -6. So I'd have a point down here somewhere. And how about we test a point between 0 and 5? How about f of 2? So that would be opposite of 2 by 2 minus 5 by 2 plus 2. That would be -2 by -3 by 4. And so that would be 6 by 4, that would be 24. So that's going to be a point way up here somewhere. And so I can get a rough sketch of the curve. I follow the end behavior. Now since we have a multiplicity 1 on x plus 2, multiplicity 1, it passes through. It's going to hit this, it's going to go through this point, -1, -6, come back up to 0, 0. Multiplicity 1, it passes through. It's got to come up through this point 224. Maybe it goes up a little bit further, maybe not. I'm not sure. Now, finding that highest point is difficult without calculus or without a calculator. So don't necessarily worry about finding those turning points. They won't always be exactly halfway between. Okay, but we're just looking for a rough sketch. It's going to come back down through 5, 0. Multiplicity 1, it passes through the point and follows the end behavior. And of course we could check our work with a calculator if we have one handy. So there's a rough sketch of the curve. So now we can sort of shorten that process a little bit if we'd like, just by recognizing patterns. Alright, so first, the y-intercept. So let's look at a new function. F of x is x minus 1 by x plus 4 by x plus 2 squared. Alright, so let's see what we have here. We have a y-intercept. Finding f of 0. F of 0 would be 0 minus 1 by 0 plus 4 by 0 plus 2 squared. That would be -1 by 4 by 4. That would be -8. We have the y-intercept. X-intercepts. X minus 1 equals 0. I have an x-intercept at 1. X minus 4, x plus 4 equals 0. So let me write that out a little bit more. Right, if I have x minus 1 equals 0, x equals 1. X plus 4 equals 0, x equals -4. X plus 2 squared equals 0, x equals -2, but I have to be careful with this one since it was an x plus 2 squared. This has multiplicity 2. I have to be careful on that one. The degree. I went a little bit out of order here. I have a degree 1 factor, degree 1 factor, and a degree 2 factor. So the degree is 4. 1 plus 1 plus 2 is 4. Leading coefficient. Well, a leading term, since I don't see any number out here, the leading term would be x to the 4th, which means the leading coefficient is 1. So that tells me that since I have an even degree, positive lead coefficient, my end behavior is up on both sides. All right, let me plot the x-intercepts at 1, at -4, and at -2. Plot my end behavior. A little bit to the left of -4, it's up. A little bit to the right of 1, it's up. All right, now, I know I have the point 0, -8. So let's just say here's -8. Now what happens? Near -4, so start from the left. Now what happens at -4? The multiplicity is 1. It passes through. What happens at -2? Now I know it's going to have to come back up to -2. 0, right, to that x-intercept. But what happens at -2? I have a multiplicity 2, so using that multiplicity 2, I know it's going to turn there. It's not going to pass through because it's an even multiplicity. It's got to come back down some. It's going to go through this this y-intercept at 0, -8. It's going to come up to x equals 1. Multiplicity 1 passes through, follows the end behavior. And there's a rough sketch of the curve. We could plot a couple other points to find some other guide points, but that's the basic sketch of the graph. Let's look at another example. Sketch. F of x is negative x minus 2 cubed, x minus 5, x plus 1 squared. All right, so we want to find a y-intercept. F of 0 will be opposite of 0 minus 2 cubed by 0 minus 5 by 0 plus 1 squared. So let's see, that would be a negative. We'd have a -2 cubed, so that's a -8. 0 minus 5 is a -5. And 0 plus 1 squared, that's 1 squared, which is 1. So this is -40. The degree. I have a cube. I have a degree of 3. Let's see, a degree 3 factor, a degree 1 factor, and a degree 2 factor. So 3 plus 1 plus 2 is 6. The lead coefficient would be -1. So considering my end behavior, the degree is 6, the leading coefficient is -1, the end behavior will be down, down. X-intercepts. X minus 2 cubed equals 0. That implies that x equals 2 with a multiplicity 3. Be careful on that one. X minus 5 equals 0. X equals 5. X plus 1 squared equals 0. X equals -1. Multiplicity 2. All right, let's sketch the curve. plot the x-intercepts. We have an x-intercept at 2, we have an x-intercept at 5, we have an x-intercept at -1. End behavior, down on the left, down on the right. I have a y-intercept at -40. Let's just say that this is -40. Here's my y-intercept. Alright, so starting from the left, we're all the way down on the left. The curve's going to come up to -1. Now what happens near -1? Well, since we have a multiplicity 2, it's going to touch and bounce off. Multiplicity 2. It's going to hit my y-intercept at -40. Now it's got to come back up to, I'm sorry, that was at -1. Now it's going to come back up to x equals 2. Now at x equals 2 we have multiplicity 3. Since we have multiplicity 3, we know the curve is going to flatten out and pass through. So flatten out and pass through x equals 2. Alright, now we could plot a point and find, some other guide point here. But what's going to happen is it's going to have to turn to come back down to x equals 5. And at x equals 5, since it has multiplicity 1, it just passes through. So there's a rough sketch of the curve. Let's turn the idea around now. Here we have this graph of a function, and we want to write the equation that models it. And so what I would do here is focus first on the x-intercepts. I have an x-intercept at -5, I have an x-intercept at -4, and I have an x-intercept at 1. So notice that means that f of -5 equals 0, which implies that I have a factor of x minus -5, or x plus 5. Similarly, I have f of -4 equaling 0, which implies I have a factor of x plus 4. And I have f of 1 equaling 0, which implies I have a factor of x minus 1. Notice that it passes straight through at each of those x-intercepts. It doesn't bounce off, it doesn't flatten out near either of them. So what that means is all of my factors have multiplicity 1. So what I can do now is write my function is some a value times x plus 5 times x plus 4 times x minus 1. And now what I do is I try to find some other nice point, maybe using the y-intercept, to figure out the a value. Using the end behavior, I expect the a value to be positive. So I'm going to focus on this point. That looks to be 0, -20, or pretty close to it. So that means when x is 0, the output is -20. So then -20 would be equal to a times 0 plus 5, 0 plus 4, 0 minus 1. So -20 is a times 5 times 4 times -1. -20 would equal a times -20, and so a equals 1, which is positive, reasonable. So then I can revise and say that I expect this function to be just x plus 5 by x plus 4 by x minus 1. Now for me, I'm happy with that answer in the factored form. Sometimes they may write the answer in its expanded form, and so if your answer doesn't look like this, if you're checking your answers in the book and it doesn't look like this, that doesn't necessarily mean it's wrong. It might mean that they just expanded the result. Let's look at another example. Now here we see this graph, and I see 3 x-intercepts at -3, at 1, and 6. So I immediately know that I have factors of x minus negative 3, so that's an x plus 3. I have a factor of x minus 1, and I have a factor of x minus 6. Notice that near negative 3, it passes through. So let's just assume that it's multiplicity 2. It doesn't appear to flatten out too much. So I'm going to go with a multiplicity 2. So that means I have an x plus 3 squared. So that means I can write a function of the form a by x plus 3 squared by x minus 1 by x minus 6. Now I need to use a test point, and sometimes it's difficult to find a reasonable test point. You can go ahead and just use, I'm going to try and use the y-intercept, and it's just going to come close, okay? My y-intercept appears to be negative, 0, negative 100, let's see, it's 25, 50, 75, 25, so negative 110, negative 120, somewhere in there. I'm going to go with negative 115. I'm really just sort of, guesstimating there. It's not going to be perfect every single time. So let's see what happens here. So I'd have then negative 115 is a by 0 plus 3 squared by 0 minus 1 by 0 minus 6. Negative 115 is a by 9 by negative 1 by negative 6. Negative 115 is a by 54. So negative 115 over 54, notice that that's about negative 2. Right? Notice that 54 times 2 is 108. So I'm going to guess that a is approximately negative 2. So my function then is f of x is negative 2 by x plus 3 squared by x minus 1 by x minus 6. All right, and one more example. Let's see what we have here. We see this graph, and I see again 3 x-intercepts at negative 4, at 1, and at 5. So that means I have factors of x plus 4, x minus 1, and x minus 5. Now, at x equals negative 4, it goes straight through, multiplicity 1. At x equals 1, it passes through but flattens out. So I'm going to guess that this is a multiplicity 3, x minus 1 cubed. At x equals 5, it does not pass through. Instead, it bounces off. So I'm going to guess that has a multiplicity 2. So I can start by writing then that my function f of x is a by x plus 4 by x minus 1 cubed by x minus 5 squared. Now, using a point, I'm going to use, it looks like it passes through 0, negative 25. So I'm going to use 0, negative 25. So then I'd have negative 25 is a by 0 plus 4 by 0 minus 1 cube by 0 minus 5 square. So negative 25 equals a times 4 times negative 1 times 25. Now, I'm going to notice how I've got both of those 25s. I'm going to divide through by 25 here. So then negative 1 is equal to a times 4 times negative 1 times negative 4. And so a equals 1/4, or 0.25. So I'm going to say then that the function f of x is 1/4 by x plus 4 by x minus 1 cubed by x minus 5 squared. All right, we'll end things up with a application. The profit of a company in thousands of dollars over a 14-month period can be modeled by the function p of x is negative 0.2x cubed plus 3.5x squared minus 12.4x plus 53.6, where x represents the time in months. We're asked to graph the given function for 0 to 14 and label the axes and show the window. All right, so let's bring up the calculator. I'll clear that out. Negative 0.2x cubed plus 3.5x squared minus 12.4x plus 53.6. We're told to graph this on 0 to 14. So 0 to 14 on the x's. And now for the y's, I'm not really sure what to do there. So I'm going to start by, I'm just going to start with negative 20 to 100. And let's use a scale of tens. And I guess the reason why I'm thinking about this is we're talking about profit. So profit can be negative or positive, and we're talking about profit in thousands. So that's I'm showing if my y max is 100, that's a profit of 100,000. I'm really just guessing right now. Let's see what the graph does. And that's actually not a bad graph. All right. So it turned out to be that I guessed pretty good. All right, so let me grab this graph and put it over here. All right, so there's my graph. All right, so label the axes. This axis is x. This axis is p of x. And I used a scale of 10. So 10, 20, 30, 40, that's 50. 60, 70, 80, 90, there's 100. So I've labeled the axes. This is 12. This is 14, right? Yeah. So 2, 4, 6, 8, 10, 12. Okay. Use the function to estimate the profit of the company after 5 months. All right, so f of 5 would be negative 0.2 by 5 cubed plus 3.5 by 5 squared minus 12.4 by 5 plus 53.6. Now, I've already got this on the calculator, so I'm going to use the calculator. I'm going to hit trace, 5, enter, and that's 54.1. All right, so that's this point right here. F of 5 is 54.1. So what does that mean? After 5 months, the company's profit was about $54.1 thousand. All right, so that's $54,100. Determine the number of months it took for the profit to reach its highest value. All right, so if we go back to the calculator, the highest value occurred at this maximum, this relative maximum. I'll calculate the maximum. At about 9.5 months, about 80.2 thousand. So after about 9.5 months, the profit reached its maximum. its highest value. And so first we're going to start with long division of polynomials. So the long division process for polynomials is similar to the long division process for integers. So what we do is we start with writing a long division format, and we write the divisor on the outside and the dividend on the inside. And with the long division process, we first do a division step. Now in the division step, we only divide by the lead term. Right, we only divide by the lead term. So we say, well, what is x cubed divided by x? How many times does x go into x cubed? X goes into x cubed x squared times, because x times x squared is x cubed. Now in the multiplication step, we multiply back through everything in the divisor using the distributive property. So that gives me an x cubed and a minus 6x squared. And now here's where the most errors are made in the long division process. The next step in long division is subtraction, but we have to subtract this entire line. X cubed minus x cubed is 0. Negative x squared minus negative 6, that's negative 1 plus 6, that's 5x squared. And now we bring down everything else, right? We bring down the rest, and we repeat the process. X divides into 5x squared. So now we're not going back to this, we're not going to the x squared. No, we're not working there because now we have this remainder. Now we're working here. X divides into 5x squared, positive 5x times. Multiplying back through the divisor using the distributive property. That's 5x squared minus 30x. Subtracting that entire line. 5x squared minus 5x squared is 0. Negative 24x minus negative 30x. That's negative 24 plus 30. That's 6x. And we bring down the rest. Minus 36. We repeat the process. X divides into 6x 6 times. Distributing back. 6 times x is 6x. 6 times negative 6 is negative 36. Subtracting that entire line. (6x minus 6x is 0). Negative 36 minus negative 36 is 0. There's no remainder. So we can write that x cubed minus x squared minus 24x minus 36 divided by x minus 6 is the quotient x squared plus 5x plus 6. Let's see another example. Let's divide 12x cubed minus 25x squared minus 9x plus 3 by 3x plus 5. Writing the long division form, 3x plus 5 divides into 12x cubed minus 25x squared minus 9x plus 3. Dividing the 3x into 12x squared is 12x cubed, is 4x squared. Distributing back 12x cubed minus, I'm sorry, that's a plus, right? 4 times 5, that's plus 20x squared. Subtracting that line. 12x cubed minus 12x cubed is 0. Negative 25 minus 20, that's negative 45x squared. Bring down the rest. Repeat the process. 3x into negative 45x squared, that would be a minus 15x. Multiplying back. negative 45x squared minus 75x. Subtracting that line. Negative 45 plus 45 is 0. Negative 9 plus 75, that's 75 minus 9, that's 66x plus 3. Repeating the process. 3 divides into 66 22 times. Multiplying back, that's 66x plus 110. Subtracting that line. 66 take away 66 is 0. 3 take away 110 is negative 107. So here we have a remainder. So when this happens, we can say that this division process yields the quotient 4x squared minus 15x plus 22, and a remainder term plus negative 107 over the divisor, 3x plus 5. Now, so we don't usually write plus and negative, so I would usually write that as 4x squared minus 15x plus 22 minus 107 over 3x plus 5. So that's the long division process. The division algorithm. So the algorithm we have just used is actually based on this thing called the division algorithm, which says that if f of x and d of x are polynomials, with d of x not equal to 0, the degree of d of x less than the degree of f of x. There exists unique polynomials, q of x and r of x, such that f of x over d of x is q of x plus r of x over d of x. That's what we did. All right. So what we saw earlier was that 12x cubed minus 25x squared minus 9x plus 3 over 3x plus 5. We divided by 3x plus 5. And that ended up being a quotient 4x squared minus 15x plus 22 plus a remainder. Plus the remainder was negative 107 over the divisor, 3x plus 5. And that's how we expressed it a moment ago. An alternative way to express it is that f of x is d of x times q of x plus r of x. So the original function, the dividend, 12x cubed minus 25x squared minus 9x plus 3. That can be expressed as the divisor, 3x plus 5, times the quotient, 4x squared minus 15x plus 22, plus the remainder, minus 107. So this is a different way to express it that sometimes we prefer. Now let's keep that in mind because we're going to be using it later. In certain circumstances, we can use another approach, another process called synthetic division. But this only works if we're dividing by a polynomial by a first degree polynomial of the form x minus c. So for example, here we have x cubed minus 2x squared minus 5x minus 6 divided by x minus 3. So we are dividing by a first degree polynomial of the form x minus c, and so in this case my c is 3. I'm dividing by x minus 3, so that's the form x minus c where c is 3. So in the synthetic division process, what we do is we kind of hold the 3 off and we build a little structure. We take the coefficients of the original polynomial, 1, negative 2, negative 5, negative 6. Draw a line. And what we do is we drop down the first coefficient, 1. We multiply. So we multiply. 1 times 3 is 3. And we add. Negative 2 plus 3 is 1. We multiply. 1 times 3 is 3. And we add. Negative 5 plus 3 is negative 2. And we multiply. Negative 2 times 3 is negative 6. And we add negative 12. And so what this tells me is that the quotient is based on those three terms, and the remainder is based on this last term. So what this tells me overall is that x cubed minus 2x squared minus 5x minus 6 divided by x minus 3 is the same as 1x squared plus 1x minus 2. Now I have the remainder, minus 12 over x minus 3. Now, we might say, well, where did I get that x squared from? If we just sort of focus on the division process, or just the lead terms, notice that I have an x cubed divided by an x to the first. Notice I have an x cubed. All right, let's try that again, starting over. Notice, if we think about the division and just looking at the lead terms, I have an x cubed divided by an x. It should seem reasonable that we're going to start with an x squared term. And then it drops down, so this is the x squared coefficient, this is the x coefficient, this is the constant, and this is the remainder. All right, let's go into a little bit more detail on that process. All right, so here's the process written out. To divide a polynomial f of x by a first-degree polynomial of the form x minus c, where c is a constant, we follow these steps. Write the coefficients in the dividend, f of x, in descending order and insert zeros for any missing terms. Determine the value of c from the divisor and set up the synthetic division. Draw a line below the coefficients, leaving some room above the line. Bring down the leading coefficient. Multiply c by the coefficient you brought down. Write this product in the second row, second column. Add the values in the second column. And then you sort of repeat that process. Multiply the divisor by the result from step 4. Write this product in the second row, third column. Add the results in the third column. Repeat the process until all coefficients have been used and all columns have been filled in. The last entry in the bottom row is the remainder of the division process. The other entries in this row will give the coefficients in descending order of the terms of the quotient, which will be a polynomial whose degree is 1 less than the degree of f of x. Let's see another example. Divide 3x cubed minus 11x squared minus 20x plus 5 by x minus 3. All right, so I can see that my c is 3. Long division. Let me set it up. I've got my 3 here. I write the coefficients. 3, negative 11, negative 25. Leave a space. Bring down the first coefficient. Multiply. 3 times 3 is 9. Add. Negative 11 plus 9 is negative 2. Multiply. Negative 2 times 3 is 6. Negative 6. Add. Negative 20 plus negative 6 is negative 26. Multiply. Negative 26 times 3 is negative 78. Add. Negative 73. So therefore, 3x cubed minus 11x squared minus 20x plus 5 divided by x minus 3 is 3x squared minus 2x minus 26 minus 73 over x minus 3. Or we can write this in the form 3x cubed minus 11x squared minus 20x plus 5 equals divisor x minus 3 times the quotient 3x squared minus 2x minus 26 minus 73. Here's another example. This one might be a good one to try on your own, but be careful. There's a couple of tricks in this one you need to be aware of. Alright, so if I want to divide x cubed minus 2x plus 1 by x plus 4, I might say, well, we can't do this because the divisor isn't of the right form. Well, yes it is. We just have to write x plus 4 as x minus negative 4. And now the c value is negative 4. Alright, so I put the negative 4 off to the side. I write my coefficients. So I have 1, negative 2, 1. Oh, wait a minute. I made a mistake. This is a degree 3. My dividend, my f of x, is a degree 3, so it means it should have 4 terms. So in descending order, I have 1x cubed, I have 0x squared, negative 2x plus 1. Leave some space, draw your line, start the process. 1, bring down the 1, multiply. 1 times negative 4 is negative 4. Add, that's negative 4. Multiply, 16, add, 14. Multiply, negative 56, add, negative 55. So x cubed minus 2x plus 1 is the same as the divisor, x plus 4, times the quotient, x squared minus 4x plus 14, plus the remainder, minus 55. The remainder theorem. Now, thinking of that division algorithm, the second form of the division algorithm with the divisor x minus c, I can write that f of x is equal to x minus c, not 6, sorry, x minus c, times the quotient, q of x, plus the remainder. And, yeah, plus r of x. Now, if we wanted to evaluate f of c, well, let's see. F of c would be c minus c times q of c plus r of c. So notice that c minus c is 0, and so that would be 0 times q of c plus r of c. And 0 times q of c, well, that's going to be 0 plus r of c. And so that's just r of c. All right, starting this part over. Let's look at this remainder theorem. Starting over to the remainder theorem. All right, now using division algorithm with divisor x minus c. Now, since we have a linear divisor, that means our remainder will end up being a constant, just be a number instead of an actual function. So we can write, using the division algorithm, that our original function, f of x, can be written as the divisor, x minus c, by the quotient, q of x, plus a remainder. Now, if we wanted to evaluate f of c would be replacing all the x's with c's. I'd have c minus c times q of c plus r. Now c minus c is 0, so I have 0 times q of c plus r. 0 times q of c is 0 plus r. F of c is r. What does that tell us? If a polynomial is divided by x minus c, then the remainder is f of c. If a polynomial is divided by x minus c, then the remainder is f of c. Let f of x equal the opposite of x to the fourth plus 4x cubed minus x minus 3. Use the remainder theorem to find f of negative 3. We could just do a simple substitution, right? Substitute negative 3 into the function and evaluate it. But wait a second, how can we use the remainder theorem? Well, this is my c. This is my c. So, if I were to remember that the f of c is equal to the remainder if I divide by x minus c. When dividing by x minus c. So if I'm dividing by x minus negative 3, if I divide the polynomial by x minus c, negative 1, 3, 7, negative 21, 63, let's see, 62, oh, careful there, Joel, 62. It's a negative 186, so that's negative 189. So the remainder is negative 189. Therefore, f of negative 3 is negative 189. I didn't have to do anything with exponents. I could just use synthetic division. Now, we can check this if we want. F of negative 3 is the opposite of negative 3 to the fourth plus 4 times negative 3 cubed minus negative 3 minus 3. So let's see, negative 3 to the fourth is 81, so negative 81. Plus 4 times negative 27, plus 3 minus 3. That's negative 81 plus, let's see, 80 and 28 is so negative 108, and that is negative 189. But I can use division to find the same result using this remainder theorem. That concludes the presentation for this section.